Today in AC electrical circuits, we're looking at lab number 6, series RC and RL circuits. Under objective, this exercise examines the voltage and current relationship in series RLC networks. Of particular importance is the phase of the various components and how Kirchhoff's voltage law is extended for AC circuits. Both time domain and phasor plots of the voltage are generated. Under reference sections, I'm referring to Sherman's Outlines, Basic Electricity, 2nd edition. Chapter 15 talks about single-phase circuits. Chapter 13 is about inductance and inductive reactance. Chapter 14 is about capacitance and capacitive reactance. So in Sherman's Outlines, Basic Electricity, Figure 14-16C is the time diagram of an RC series circuit, like we're going to be building today. And I just want to remind everybody that VR, the voltage across the resistor, and the current share the same phase. So we'll not be able to see current on the oscilloscope, but we can see the voltage drop across the resistor on the oscilloscope. And the phase angle of the voltage across the resistor is identical to the phase angle of the current flowing through the resistor. I just want to remind everybody that the voltage across the capacitor lags I by 90 degrees. So that means it's going to lag VR by 90 degrees. So you can see the voltage on the capacitor is 90 degrees out of phase from VR. And figure 14-17 is for a series RC circuit, and we can see that R is at 0 degrees, XC is at minus 90 degrees, and Z is the total AC resistance, so it's going to be at some angle from R. You can see figure 13-12 shows us the timing diagram of an RL series circuit. So I just wanted to remind you that VR, the voltage across the resistor, will share the same phase as the current. So we can't see current on the oscilloscope, so the phase angle for the current will be the same as the phase angle for the voltage across the resistor. Now VL is going to lead I by 90 degrees. That means the voltage across the inductor is going to lead VR by 90 degrees. So that's what we're looking for when we look on the oscilloscope. Figure 13-13 shows us the phasor diagram for an RL circuit, and you can see R is at 0 degrees, XL is at 90 degrees, and Z, which is the AC resistance component of the entire circuit, is going to be at some angle to R. And in chapter 15 they talk about single-phase circuits, and they talk about RLC in series, which is what we're going to be working on today. And in figure 15-1 they give us the RLC circuit diagram, phasor diagram, and voltage phasor triangle for when XL is greater than XC. So this is basically an inductive type circuit. And in figure 15-2 they give you the phasor diagram and voltage phasor triangle for when XC is greater than XL, basically a capacitive circuit. And they provide you with the formulas that we're going to be using in the lab today. They cover impedance in a series RLC circuit, And figure 15-4 gives you the series RLC impedance phasor triangles. We have a brief theory overview stating that each element has a unique phase response, so we need to keep this in mind when we're doing our calculations and viewing the output signals on the oscilloscope. The equipment today is going to be the AC function generator, and we use the circuit test SWF7000. We're going to be using the Tektronix oscilloscope, so you'll either use the TDS210 or the TDS1002. And we're going to use a digital multimeter, and as always we use the Mastech MSM9803. We're going to be using three components today: the 1K ohm resistor, the 10 millihenry inductor, and the 10 nanofarad capacitor. So the 10 millihenry inductor is going to be labeled 103, and the 10 nanofarad capacitor will be labeled 103. My 1K ohm resistor is actually 995 ohms. My 10 millihenry inductor is 22.3 ohms. And my 10 nanofarad capacitor is actually 13.45 nanofarads. So under equipment, you can see I've filled in the model numbers, and I haven't bothered with the serial numbers. And I've recorded my values for the 1K ohm resistor, the 10 millihenry inductor, and the 10 nanofarad capacitor to make sure that I have the right components. Under schematics, we have figure 6.1, which is R and C in series, and in figure 6.2 we have R and L in series. Under procedure, step number 1, we're talking about the RC circuit, so we're going to be using figure 6.1 with Vin equals 2 volts peak to peak sine wave at 10 kilohertz. Our resistor is going to be 1K ohms, and our capacitor is going to be 10 nanofarads. We're to determine the theoretical capacitive reactance and circuit impedance and record the results in table 6.1. The experimental portion of this table will be filled out in step 5. We're then going to be using the voltage divider rule to compute the resistor and capacitor voltages and record them in table 6.2. Just a reminder, phasors are in RMS, but the oscilloscope gives us volts peak to peak, so we're going to leave our results in volts peak to peak. So I've created two calculation pages for you. The first part is for the RC circuit, where R equals 1K, C equals 10 nanofarad, Vn equals 2 volts peak to peak, and the frequency equals 10 kilohertz. I've already put the formulas in for you, and the formulas in for the voltage divider rule. So these are the calculations for the RC circuit, and I just wanted to mention that you have to follow the order of operations, so I've actually put parentheses around my items that I'm going to do the 1 over function of. So it's 1 over all of those things, so put parentheses or brackets around the entire thing. Same thing when you're doing the square root for the circuit impedance. Make sure that you put parentheses around them so that the order of operations stay intact. Most calculators don't have an arctan button, they have a tan to the -1 button. And remember to put parentheses around those two numbers when you're dividing them. We're going to use voltage divider for VC and VR, and remember these are phasor numbers, so we need RMS values. So it's 2 volts peak to peak divided by 2 gets us to the V max, or the peak voltage, and then divide by the √2 to get to the RMS voltage. And then for my answer, I leave it as 1.69 volts peak to peak divided by 2 root 2, because this is what we're going to see on the oscilloscope. So if you divide by 2 root 2 now, when you take the reading off the oscilloscope, you'll have to divide it by 2 root 2 to compare the two. So I just leave all my voltages as peak to peak. That way it makes it a lot easier for me to compare it to the voltage off of the oscilloscope. So under data tables for RC circuits, I've filled in my values for XC, the Z magnitude, the Z phase angle, VC magnitude and phase angle, VR magnitude and phase angle. So under procedure, RC circuit, step 2, we're going to build the circuit of figure 6.1. We're going to place one of our oscilloscope probes across the generator and the other across the capacitor. Set up our function generator at 2 volts peak to peak, 10 kilohertz. So this is my circuit wired up on the trainer, and I've decided to use 3 binding posts. The white binding post with the red lead coming off of it goes to the 1K ohm resistor, and that's where I'm going to plug in the function generator and channel 1 of the oscilloscope. The yellow terminal, which has this yellow wire connected to it, runs out to the midpoint of the capacitor and the resistor. I have my 103 capacitor, and on the other side of my capacitor is the ground lead, or the black lead, that goes to my orange binding post, and that will go to the black banana lead coming from the function generator, the black banana lead coming from channel 1 of my oscilloscope, and the black banana lead coming from channel 2 of my oscilloscope. I just want to show everybody that coming out of that yellow terminal, you can see the wire pokes out on the other side, and I have a bit of bare wire on this side. Same thing with my red terminal, same thing with my orange terminal. I always leave a little bit of wire exposed so that I can see I've got good metal on metal contact. So over on my binding post, you can see I have the input from the function generator and channel 1 oscilloscope, channel 2 oscilloscope, and all the black banana leads stacked together. So those are all the grounds or common points. So remember, the BNC connector goes to the output of the function generator. All the knobs should be pressed in. This one should be fully counterclockwise till it goes click. You want the power button on. You want to select sine wave. You want the range to be times 10K. You want the OSC button in the out position. So we're going to rotate the big knob until we get as close as possible to 10.00. And we want the little indicator light to be on where it says kilohertz. So under procedure, step number 3, we're to measure the peak-to-peak voltage across the capacitor and record it in table 6.2. Along with the magnitude, be sure to record the time deviation between VC and the input signal, from which the phase may be determined. We're going to be using the math function, measure and record the voltage and time delay for the resistor. And they show us that this is going to be equal to Vin minus Vc. They want us to compute the phase angle and record these values in table 6.2. So over on my oscilloscope, make sure that channel 1 is on AC coupling. We want to turn the bandwidth limit on. Volts per division should be coarse, probe is times 1, and the invert is off. On channel 2, coupling should be AC. We want the bandwidth limit on. Volts per division coarse, probe 1 times, invert off. Pressing the measure button, we'd like channel 1 frequency, channel 1 peak to peak, channel 2 peak to peak, and we're not worried about the others. Pressing the channel 2 menu button brings up the menu. Pressing it again takes away channel 2. We would like our waveform to cross in the center line here. It'll make all our readings a lot easier for us. So you can see I have my horizontal position set to the 0 line. And this little arrow is controlled by the trigger level knob. So I've adjusted the trigger level just down a little bit so that my 0 crossing is right on the 2 0 lines. I'm going to bring back channel 2 and press the measure button so that I can record channel 2 peak to peak as 1.62 volts. Now the next thing I want to do is measure this phase delay. So I want to see how far out of phase this particular waveform is. So in order to do that, I know one complete waveform is 360 degrees. The formula we use to compute phase angle is delta t, or the change in time from one waveform to the other, divided by the period times 360 degrees. So if I take the change in time over the total period times 360 degrees, that will give me my phase angle here. Now in order to figure out what that is, I'm going to use the cursors. So I'm going to press the cursor button, and right now it's type off. Now it's type voltage. Now it's type time. So I'm going to use the cursor position knob, and I'm going to move my first cursor over to the first 0 crossing line. Then I'm going to move my second cursor over to the second 0 crossing line. And you can see my delta is 10 microseconds. Now I would like to get this to be as accurate as possible. So to do that, what I'm going to do is I'm going to change the volts per division for channel 1. So I'm going to rotate the knob clockwise until it's almost vertical in nature. And then I'm going to do the same thing for channel 2. So now I've got 2 vertical lines crossing my 0 line. Now I'm going to change the seconds per division and now I'm going to use my horizontal just to move the waveforms back a little. Now I'm going to press the cursor button, and I'm going to change my channel 1 cursor to make sure that it is going through that 0 crossing. And then my channel 2 cursor position until it goes through the second waveform. And you can see I'm getting a more accurate reading of 9.2 microseconds. So over here on table 6.2, I've filled in BC experimental magnitude as 1.62 volts peak to peak, which is similar to my theory magnitude. My experimental delay was 9.2 microseconds. Remember that the frequency was 10 kilohertz, so the period being 1 over the frequency is 100 microseconds. So to calculate this experimental phase angle, you take the 9.2 microseconds, divide it by the 100 microseconds, times 360 degrees, and you end up with 33.12 degrees. In theory, it was 32. Experimentally, it was 33. Now, where does this negative sign come from? So I have to rotate my seconds per division knob counterclockwise until I get several periods showing up on the screen. And then I'm going to reduce my volts per division for channel 2 and my volts per division for channel 1 until the waveform is back on the screen. I might have to readjust my horizontal position to get my waveform going through the zero crossing lines. So here you can see this is the input voltage, and this is the voltage across my capacitor. So you can see the voltage across the capacitor lags the input voltage by so many degrees. So that's where the minus sign comes from. So in table 6.2, I've put the minus sign in front of my 33.12 degrees. Now to find the voltage across the resistor, we're going to use the Math menu button, and the operation is going to be minus, and it's channel 1 minus channel 2. Now it's very important that when you do this, both your channel 1 and your channel 2 are on the same volts per division, or else the math will not be calculated correctly. Now we can see that the waveform that went through the zero line is actually our applied voltage. The voltage across the capacitor lagged the input voltage. So the voltage across the resistor must lead the input voltage, and it must lead the voltage across the capacitor by 90 degrees. So we want to know what the phase difference is between the voltage that was applied to the circuit and the voltage that's on the resistor. So to do that, I'm going to turn off channel 2 by pressing the channel 2 menu button twice, and now we've eliminated the voltage across the capacitor. Now when we press the measure button, you'll notice we can see channel 1, and if I press the first button on the menu, I have source channel 2 off, or source channel 1. I don't have the option of source channel math. So I'm not going to be able to read the volts peak to peak from the measure menu across the resistor. So I'm going to use the cursors. So press the cursor button, and they were on type time, so I'm going to change it to type voltage, and using the vertical positions for cursor 1, I'm going to move the cursor to the bottom of the waveform for VR. And then for the cursor 2 position knob, I'm going to put it on the top of the waveform for VR. Now you can see my delta is 1.08 volts. That's 1.08 volts peak to peak. Now I need to record the phase angle, so I'm going to change my cursors to type time. And the first cursor is now going to go through VR where it crosses the 0 line, and the second cursor will go through the applied voltage where it crosses the 0 line. Now, to get as much accuracy as possible, I'm going to increase the sensitivity of the volts per division for channel 1 and for channel 2. Now when I do that, notice how it screws up my waveforms. That's due to the math function. So you have to make sure that your waveform stays on the screen. So the best thing I can do to measure the phase angle is change my volts per division to 200 millivolts and make sure that they're both set at 200 millivolts. And then I'll change my seconds per division just to get a little better space between the two waveforms. So now I'm going to press the cursor button, make sure they're on type time, and cursor 1 is going to go through the VR 0 crossing line, and cursor number 2 is going to go through the applied waveforms 0 crossing. And you can see my delta is 14.8 microseconds. And I just want to remind you that when it's on this side of my applied voltage, it's plus. So this is a positive phase angle. So in table 6.2, I've recorded my VR experimental magnitude is 1.08 volts peak to peak, and my experimental delay for VR was 14.8 microseconds. And using the formula I used before, 14.8 microseconds divided by 100 microseconds times 360 degrees equals 53.28 degrees, which is close to my 57.83 degrees. Under procedure, step number 4, it says with the oscilloscope displaying Vin, Vc, and Vr, we're to sketch the waveforms on oscilloscope plot number 6.1. So this is the waveform we're supposed to sketch. I highly recommend you'd start by turning off the math menu and then turn off channel 2 and start by sketching just channel 1. So I start by putting a dot at my 0 crossings, and then a dot at my peak, a dot at my next 0 crossing, a dot at the negative peak, a dot at the 0 crossing, and then I try to put in a curve at the top and a curve at the bottom. And make sure you label your first waveform as Vin. Then bring in your second waveform and notice that there is a phase shift and the peak points are going to be lower. So this is the voltage across the capacitor. I recommend you draw that in second. So here's my second waveform drawn in, and it's Vc. Now to draw VR, put the math menu back on again and turn off channel 2. Now you can see the input voltage versus the voltage across the resistor, and now you can sketch that in. So this smaller waveform is the voltage across the resistor, so I've labeled it VR. So under procedure, step 5, they want us to compute deviations between theoretical and experimental values in table 6.2. And what we're going to be doing is, based on the experimental values, they want us to determine the experimental Z and XC value via Ohm's law. So I equals VR divided by R, XC equals VC divided by I, and Z is equal to Vin divided by I. And we're supposed to record these into table 6.1 along with the deviations. So that sounded like a lot to do, but all we have to do is take I is equal to VR divided by R, and then XC is equal to VC divided by I, and Z is equal to Vin divided by I. So all we're doing is taking the experimental magnitudes. So I ends up being equal to VR, which is 1.08 volts, divided by the resistance reading we took actual. Mine turned out to be 995 ohms. So I ends up being 1.085 milliamps. Now keep in mind, 1.08 volts is peak to peak, so the milliamps will also be peak to peak. So XC is equal to VC, which was 1.62 volts, divided by the current of 1.085 milliamps, equals 1.493 k ohms. And Z is equal to the 2 volts peak to peak we put into the circuit, divided by the current, which was 1.085 milliamps, and that's equal to 1.843 k ohms. So you can see in my table, experimental XC is 1.493 k ohms, and Z magnitude experimental was 1.843 k ohms. So they're very close to what we calculated in theory. Now the experimental theta comes from the formula theta equals arctan minus VC over VR, and on your calculator it's probably labeled as tan minus 1, and that's of minus 1.62 volts divided by 1.08 volts, and that ends up equaling minus 56.31 degrees, which is close to the 57.83 that we calculated. Under procedures, step number 6, we're to create a phasor plot showing Vin, Vc, and Vr on Phasor Plot 6.1. Remember, phasors are in RMS, but the oscilloscope gave us volts peak to peak. So at this point we must convert our answers using V peak to peak divided by 2 root 2. So the first steps in drawing a phasor diagram is to convert your voltages to RMS voltages. To do that, you divide the peak-to-peak voltage by 2 root 2. So for Vin, I had 2 volts peak-to-peak. That means I have 1 volt peak coming in, and you divide that by root 2, and you end up with 0.707. or 707 millivolts. Do the same thing for VC, and your 1.62 volts becomes 573 millivolts RMS. So your phasor diagram in plot 6.1, VR and I are on the horizontal axes. Current is the reference in a series circuit, so VR and I gets plotted on the same horizontal axes. VR happened to be 382 millivolts, and I happens to be 384 milliamps, so they're both about the same vector size. VC is always at minus 90 degrees from VR, so that's straight down, and it was 573 millivolts, so I went down almost 6 divisions. Vin, which was 707 millivolts, can be drawn by filling in the box from the two arrowheads and then drawing in your line. The angle from VN to VR is plus 53 degrees. The angle from VN to VC is minus 33 degrees, and the two add up to almost 90 degrees. So I'm going to leave it up to you to calculate all the deviations for table 6.1 and 6.2. So under procedure, step number 7, we're now working with the RL circuit. So we're to replace the capacitor with the 10 millihenry inductor, and we're now using figure 6.2, where R is in series with L. We're to repeat steps 1 through 6 in a like manner, using tables 6.3 and 6.4, and sketch the oscilloscope waveforms and phasor diagrams on plot 6.2. So you notice on the schematic, figure 6.1 and figure 6.2 look almost identical, except we're going to replace this capacitor with the inductor in our circuit. So this is my circuit wired up, and you can see I've replaced the capacitor with the inductor, and everything else remains identical. So these are my calculations for the RL circuit, and once again I want to remind you to put brackets around your numbers so that you can keep the order of operations intact. And when you get down to the voltage divider for the RL circuit and we calculate VL and VR, I just want to remind you that I left my answers as peak-to-peak voltages divided by 2√2, so that I can compare these to the oscilloscope readings. So on table 6.3 and 6.4, I've filled in my calculations for the RL circuit: XL, Z magnitude, and Z theta, and VL magnitude and theta, VR magnitude and theta. So you can see on the oscilloscope screen, this is my input voltage, and it's approximately 2 volts peak to peak. This second waveform is the voltage across the inductor, and it's being measured as 1.02 volts peak to peak. To find my phase angle between the two waveforms, I'm going to turn on my cursors, and I want them to be type time. So my first cursor is going to go to the first zero crossing. My second cursor is going to go to the input waveform zero crossing. And you can see my delta is approximately 17 microseconds. So to get more accuracy out of my phase angle, I'm going to increase the sensitivity on the volts per division until my waveforms are almost vertical. And then I'm going to change my seconds per division to open up the waveform. And then I'm going to reposition my cursors. So that they're going through the zero crossings. That's very important that both waveforms share the same zero line. So you can see the zero line for channel 1 is underneath the zero line for channel 2. So very important they share the same zero line. You can see my delta is 15.8 microseconds. That's a lot more accurate than I had before. So in table 6.4, for the VL line, my experimental magnitude was 1.02 volts peak to peak, which is very close to the 1.06 that we calculated in theory. My experimental delay was 15.8 microseconds. So when I take the 15.8 microseconds and divide it by the 100 microseconds, and multiply it by 360 degrees, I come up with 56.88 degrees, which is the same as the 57.86 that we calculated earlier. I just want to remind everybody that this is our input voltage, and that's our 0 point. So you'll notice this waveform across the inductor is leading. If it was on this side, it would be lagging. So on this side, it's leading. So the voltage across the inductor is leading our input voltage. Now, to measure VR, we're going to put the math menu on. The operation is minus, and it's channel 1 minus channel 2. So it's the input voltage minus the voltage on the inductor gives us the voltage on the resistor. It's also very important that when you're using the math menu, both channel 1 and channel 2 are set to the same volts per division. I'm going to remove the voltage across the inductor by pressing the channel 2 menu button and pressing it again. So that's the voltage across the inductor is gone. And now you can see my second waveform is the voltage across the resistor. To find out what its peak-to-peak value is, I'm going to put the cursors on, and they're going to be on type voltage. So the first cursor needs to go to the bottom of the smaller waveform, and the second cursor needs to be adjusted to the top of the smaller waveform. And you can see the delta is 1.62 volts. That's the voltage drop across the resistor. Now to measure the phase angle, and you notice the phase angle comes after the main wave, so it's lagging, so it's going to be negative. I'm going to change my cursors to type time. And I'm going to move the first one over to the 0 crossing line. And the second one I'm going to move over to where the math line, or the voltage across the resistor, crosses the 0 line. You can see I'm getting about 9 microseconds. I'm going to increase the sensitivity on the volts per division. I can't do it too much. So I'm going to change it to 200 and 200. Remember, they both have to be the same, and the waveforms basically have to stay on the screen, because if they go off, they start making funny shapes. And now I'm going to adjust the seconds per division to open up that waveform. Then I can move my cursors through the 0 crossing lines. And sometimes you have to kind of judge where the center of a thick line is. So you try and get as close as possible to the center of the thicker lines where it crosses the 0 line. And here you can see I've got a delta of 8.7 microseconds. So under table 6.4, I've recorded my experimental magnitude for VR as 1.62 volts peak to peak. My experimental delay was minus, remember it was lagging, so it's minus 8.7 microseconds. And using the formula, delta t over the period, I have minus 8.7 microseconds divided by 100 microseconds times 360 degrees, and that works out to minus 31.32 degrees. which is close to my 32.14 that we calculated earlier. So in table 6.3 we want our experimental XC, Z magnitude, and Z theta. So I just want to remind you that I is equal to VR over R. XL is equal to VL divided by I. And Z is equal to Vn divided by I. So I is equal to 1.62 volts, which is VR, divided by 995 ohms, which is the measured value of our 1K ohm resistor, and that's equal to 1.628 milliamps. Now keep in mind, these are peak-to-peak values. So XL is equal to VL, which is 1.02 volts, divided by the current of 1.628 milliamps. That equals 626 ohms. Z, which is our impedance or AC resistance, is the Vin, which is 2 volts peak to peak, divided by our current of 1.628 milliamps, and that works out to 1.229 K ohms. Lastly, to calculate the phase angle, it's equal to arctan of VL over VR, and on your calculator it's probably a button labeled tan minus 1 of VL, which was 1.02 volts, divided by VR, which was 1.62 volts, and that equals 32.196 degrees. So I've filled these results in table 6.3. I'll leave you to calculate the percent deviations. When sketching your oscilloscope plot, I suggest you start with Vin and then draw the voltage across the inductor. So turn on channel 2. Then press your Math menu button to get VR and turn off the voltage across the inductor. Remember to put in your volts per division for both channels, as well as the seconds per division. And remember to label Vin, which is the waveform that will go through your zero crossings and acts as the reference for VL, which should be leading, and VR, which should be lagging. So remember, Vin, VL, VR, and I were all in peak-to-peak readings. So to put these in the phasor form, we have to convert our peak-to-peak voltage into RMS voltages, so we divide them by 2√2. So Vin becomes 0.707 or 707 millivolts. VL becomes 360 millivolts. VR becomes 572 millivolts. And our current becomes 575 milliamps. So when plotting these, remember that VR is in phase with I, and the current is the reference in a series circuit. So VR and I, which are basically the same values of 572 versus 575, so both VR and the I lines are drawn along the horizontal axes. VL is at 90 degrees to VR, and VL was 360, so that's almost 4 divisions up. And Vin is 0.707, and if you square in the box, that's where the reference line for Vin comes. And you'll notice VR is minus 31 degrees from Vin, and VL is plus 57 degrees from Vin, and 57 plus 31 happens to equal about 88 degrees, which is close enough to 90 degrees. So this is your phasor diagram in plot 6.2. As with all labs, we have some questions to be answered at the end. In this case, we have 4 questions, and the answers will be based on your results. When you've completed your lab, show it to your instructor so that they may initial it to indicate that it is complete.